Now, one example. Let A be the set of all triangles in a plane and let R be a relation in A defined by R is equals to delta 1, delta 2. These are two triangles such that triangle 1 is congruent to triangle 2. Show that R is an equivalence relation in A. So our relation is triangle 1 is congruent to triangle 2. Okay, so we'll start with reflexive. First we'll check whether it is a reflexive relation or not. Let delta be any triangle in set A. So every triangle is congruent to itself. Each triangle is congruent to itself. So we can write that triangle is congruent to itself. It means delta belongs to R. So as per the definition, R is reflexive. Second is symmetric. To check whether it is a symmetric relation or not, let triangle 1 and triangle 2 are in A such that triangle 1 and triangle 2, this ordered pair belongs to R. So if delta 1, delta 2 is in R, by the definition, what it means? That triangle 1 is congruent to triangle 2. So if triangle 1 is congruent to triangle 2, we can say that triangle 2 is also congruent to triangle 1. So as per the definition, we can say that delta 2 comma delta 1 also in R. So this was in R. It shows that delta 2, delta 1 is also in R. It means R is symmetric. Now, the third one is transitive. To show that this relation is transitive, we'll consider three triangles. Let delta 1, delta 2 and delta 3 are in A such that if delta 1 comma delta 2 belongs to R, it means triangle 1 is congruent to triangle 2 and triangle 2 comma triangle 3 belongs to R. It means triangle 2 is congruent to triangle 3. Now these two relations, that triangle 1 is congruent to triangle 2 and triangle 2 is congruent to triangle 3, these two relations together show that triangle 1 is congruent to triangle 3. So when triangle 1 is congruent to triangle 3, it means we can say that delta 1 comma delta 3 also in R. So these two were there and we have found that delta 1, delta 3 is also in R. It means R is transitive. So when our relation is reflexive, symmetric and transitive as well, it is an equivalence relation. Now we'll discuss one more example. Now the second example, let Z be the set of all integers and let R be a relation in Z defined by R is equals to AB such that A minus B is even. Show that R is an equivalence relation. So we'll go step by step. First step is we'll check whether it is a reflexive relation or not. To show that, let A be any element in Z, means I'm considering that A is any integer, then what will be the value of A minus A? That is 0. And we can consider 0 as an even number, which is even. It means A comma A type elements are in relation R, which shows that R is reflexive. Now, the second relation is symmetric. We'll check whether it is a symmetric relation or not. For this, let A comma B belongs to Z such that AB belongs to R. It means A minus B is even as per the definition. If A minus B is even, we can say that negative of A minus B is also even. If you open the brackets, it will become B minus A is even. It means BA belongs to R. So AB was in R, and we have shown that BA also belongs to R. It means R is symmetric. Now the third type, that is transitive. We'll show this relation is transitive. For that, let A, B and C are in Z such that AB belongs to R. It means A minus B is even, and BC belongs to R. It means B minus C is even. Now with help of these two results, we have to show that A minus C is also even. For that, these two are even numbers. If we add them, right? If we add them, so A minus, this means that A minus B plus B minus C is also even. If you open the brackets, this B and B will be cancelled out. It means what is left? A minus C. A minus C is even. If you look at the definition, A minus B is even, it means AB belongs to R. So A minus C is even, it means ordered pair AC also in R. So it means this relation is transitive as well. R is transitive. So R is reflexive, R is symmetric, R is transitive. We can say that R is an equivalence relation.